Okay, and welcome to this next video from the series on logs and exponentials, and this is a video that's going to contain a fairly groovy trick for converting what looks like an absolute shock of an equation to something we can actually deal with by taking a curve and turning it into a straight line using logs. Sound exciting? I suspect so. So here we go. Right, so we're going to use logs to transform non-linear graphs of the form y equals ax to the n into linear graphs, and we're going to use an example just to kind of hang the whole thing on. So here we go. Right, we're talking about skid marks made by tyres on a particular road surface. And once we've stopped giggling at the phrase skid marks, we can get on with our maths. Right, so we've got the speed of a car, let's say in kilometres, and the length of tyre mark it has left on the road in terms of centimetres. And if we start off by plotting that, you can see what we've got is a curved graph. So we've got some kind of relationship going on between the two variables, and we've got to kind of figure out what that relationship looks like. And we can see straight away it's not linear because it's a curve. So we need some form of polynomial. And what I mean by that is maybe an x squared or an x cubed, x power 4, whatever it is. We've got to find some kind of curve to fit. So what I'm going to do is suggest that the length of the tyre mark is going to be a multiple of some kind of polynomial. And this, let's say here, n would be squared, cubed, whatever. It might be a non-integer. We've just got to figure out what those values are for a and n. Those are the two things that are going to be constants that we need to work out. L and s are the two variables that we are plotting against the length of the mark against the speed. Now the problem is it's a bit of a trick trying to work it out from a curve. I'm not quite sure how you go about doing it with it just looking like that. So what we're going to do is we're going to come up with a different way to be able to come up with our values for a and n, and we're going to do it by turning this thing into a straight line graph. Because if we can do that, then we can start working with our straight line graph with gradients and intercepts, and life becomes a whole lot easier. So here we go then. There's our relationship that we're suggesting. Just point to note that in the exam, generally speaking, they would suggest to you what form the relationship is going to be in, rather than you having to come up with it yourself. So we've got that. That'll be given to you and say, okay, right, what I'm going to do is take the logs of both sides. There we go. Log L equals log A S to the n. And so now what we're going to do is on that right hand side, split that up using our log laws, which is the multiplication law. So that right hand side becomes log A plus log S to the power n. And then also using law 3, we're going to bring that n to the front. And so we've got is our relationship looking like that. Now, it might be that's not looking a whole lot more simpler. And you've got a note on the screen there saying this is the form of the equation of a straight line. You're probably looking like going, how the heck is that a straight line? Well, let's just have a little look at what is going on. Equation of a straight line, y equals mx plus c. Is this thing the same? Okay, let's start off on the left. There you go. Let's equate kind of the y to the log L. It's just kind of a variable, something we're going to plot on the vertical axis. In a normal line, we'd be plotting a y coordinate. Here we're plotting the log of the length of the mark. We've then got this thing here. Now a is just a number, so therefore log a is just a number. So that thing there is a constant. So that's kind of similar to my c from my y equals mx plus c. And then the other bits I've got is the m. That bit there is going to be the gradient. And the log s is the other variable. The s, the speed the car is going at, is the variable. That's the thing that's going to be plotted along the bottom axis. And so that's kind of working like our x. So you can see with the way I've set that up there, that is a straight line equation. Log a is a constant, n becomes the gradient, log s is the variable you're plotting on the bottom axis. So what we're going to do therefore is plot, take logs of L, logs of S, plot those, and if that gives us a linear graph, which it will, we can then start doing some calculations to work out n, which is the gradient, and the intercept, which is log a. Now, all of that's going to make a whole lot more sense when we look at that in the context of our values. So here we go. That's what we're going to work with. So originally we had that equation. Now we're going to turn it into that equation there. So that's what we had to begin with. We had our values for the speed and the length of the tyre mark. And we're going to take, instead of S and L, we're going to go for log L and log S. So we're going to plot those values there. So I've used base 10. It really doesn't matter what base to use, but we might as well just use 10. It's the simplest one. Your calculator defaults to. So now what I'm going to do is plot that graph. You see what I've done is plotted these values across the bottom. So you can see my scale is now going from 1 about 1.8, just hidden under here is a 2. And then log L at the side, going from, my scale's going from 2 to 3.4, 3.6. There we go. So I've just plotted those values along the bottom, those values against those values up the side, and you can see it has turned that graph, that curved graph, into a straight line. What we've got to do now is try and figure out our values of A and N. So I'm just going to shift that graph out of the way. I'm going to start doing some calculations. First one is gradient. What I'm going to do is just pick 2 points and do the old y2 minus y1 over x2 minus x1. Rise over run, change in this case log L over change in log S. So if I put those in there, there it is. There's effectively on the top the rise, on the bottom the run using the coordinates. I end up with a value of 1.949, and that's going to be my value for n. So straight away from that, I've managed to get my n value, that's my gradient. Let's now have a look at our equation of the curve y equals mx plus c. Standard stuff, if you're putting it in, what you do is going to just pick a coordinate that's on the line. In this case, I'm going to pick this coordinate down here. I know my gradient, I got that here, 1.494, so what I'm going to do is plug all that information into the equation of a straight line. There we go. So we've got 2.92, that's that thing there. There's the gradient, there's the equivalent x value, and that allows us to work out c. And so I've got c equals minus 0.244. Now, if you plot this on a graph, one other option, of course, would just be to continue your line along and just draw it straight off, although that's not going to work particularly on the one I've got on my screen because I haven't got the negative values on there. So I've done it via calculation in this case. But what we've got is a value of c minus 0.244. And so therefore that means log a is minus 0.244 because the log a is the constant thing in my version of the equation up here. If log a equals that thing, we've got to get a, so let's just reverse the logs now using base 10. So we've got a equals 0.570. And so now we've found the two values that we're after. So that curve there, going back to our original equation where we had, that's our original format, L equals 0.570s to the power of 1.949. And there you go. Now, last thing to note is we've put a blue line, sorry, that blue comment at the bottom, just to say, well, in the normal course of things, you wouldn't expect it to be a perfect fit like it has been in my example, because you're going to get experimental error somewhere along the way. So in which case you'd be looking at a line of best fit, and you'd be basically doing exactly the same thing again. And we can look at that, and that will actually pop up actually in the stats course in year 2. Okay, so let's just summarise what we've just talked about. This next slide is pretty much standard stuff that it might be like. So it's a couple of marks in the exam, and it's going to be the same pretty much every time. So we've got an equation in the form y equals ax to the power of n. Don't get hung up on the kind of whether it's y's and x's or l's and s's. It's just, it's something in that format. And so what we've got to do is go through that process that we saw earlier in the video, where we take logs of both sides, separate them out on the right hand side, use your power law, law 3, to bring that down. And there you go. So that would be a question that says, like, can I prove that this relationship here can be written as a linear relationship using logs? And that's what you need to do. So what that tells us is we're going to be, if we were to plot these values on the graph, we'd be plotting log y against log x. The gradient is n. The y-intercept is log a. And there we go. We've got it all sorted.